Okay, the second approach to correlation is a relatively recent one. All the early approaches came about in the 1930s. This one came about 40 years later. This is called density functional theory. It's based on a set of proofs. The most important proof is that the exact energy that you can get from solving the Schrödinger equation may be expressed exactly as a function of the electron density. Now, I don't know what that function is. There are some clues to what that function is, but you can actually prove that if you knew what this function was, you could actually write a formula which says exact energy equals some function of the electron density. That took a while for people to understand that it really was important. It finally got a Nobel Prize in the late 1990s. That's a very simple idea, but it's extraordinarily powerful. Why? It's powerful because evaluating something which involves the density is the third power, maybe the fourth power of the number of functions. Compare this to good wave function-based correlated methods, which are the seventh power. There are ones that are much worse than that. So you automatically gained several orders of magnitude in what you can do. And what this suggests is if you could ever find this function, you'd actually be able to solve the Schrödinger equation exactly. Okay? Now, the big problem is that you really don't know what the function is. And you have no clear path to going from one guess to a better one, You have a clear path of going from one guess to a different one, but it's not necessarily better. All viable density functional methods, and so I'm excluding all the ones in the first decade of its life, are parameterized. The early ones were parameterized with using a small amount of experimental data. All the modern ones are parameterized using high-level correlated data. It's much more consistent. The number of parameters is actually, in modern ones, goes from maybe 10 or 12 to 50. So these theories really shouldn't be called ab initio from the beginning. They really are empirical. But they have a fundamental notion that in the limit, they're exact. Okay? Now, how do you choose a function? The advent of density functional theory made nomenclature of this computational chemistry area very much more difficult, because instead of just having to specify a basis set, I now have to specify some form. I'm going to introduce 7 functionals, and I'm going to carry those through a little bit with when I talk in the second thing about how good things are, and then I'm finally going to get down to maybe one or two functionals when I talk about confirmation and NMR and things of that nature. They're all going to start with what I call the generalized gradient approximation. What this says is that my function, unknown, is a function of density plus its gradient. Okay, so I'm not going to start, all the early ones were just functions of the density. It was pretty rapidly noticed that you at least have to put the gradient in there. So this is now a function of the density and the gradient. That's where I'm going to start. And then what I'm going to do is to say, well, let's compute some things and use those to parameterize these nature of the functions. Okay? It gets rather messy. There are functions that are simpler than the ones that I'm going to talk about. They're not very good, and I'm not going to talk about them. And there are ones that are more complicated. I'm not going to talk about those either. Okay, the first set is called the global hybrid generalized gradient approximation. As I said, the nomenclature is terrible. I'm going to give you a diagram in a couple minutes, which we'll try to make it a little easier. What this says is that the function is going to contain not only some magical parts parameterized, but they're going to contain some percentage of the Hartree-Fock energy or exchange energy. So the function is going to be two parts. It's going to be a part of the Hartree-Fock, so I'm going to have to calculate that, and then a part of something I'm going to parameterize to. The most common of these, and probably the most commonly used density functional, is called B3LYP. The B stands for Becky, the LYP stands for Li-Yang-Par, so it's random nomenclature. The 3 stands for, it only incorporates 3 parameters, so it's pretty primitive. This is still remarkably used. I'm going to try to discourage this a little bit later. It's quite good in some places, but it's quite terrible in others. There are some recent changes to this. There's something called B3LYP-D3, which puts in an empirical, so it's free, term to account for so-called non-local or dispersion interactions, interactions of atoms that are far apart. Okay. The second one is the class which I think is probably the best of the classes. These are called range-separated hybrid generalized gradient approximation. Terrible nomenclature. It's exactly the same as the previous one. Two differences. The first difference is that we're going to put in the Hartree-Fock exchange, but it's going to be put in as a variable, it's a parameter. We're going to vary it depending on basically electron distance. So that's the first thing. The second difference is that I'm going to seriously parameterize this. Instead of using 3 parameters, which really is not enough, I'm going to use a larger number. These are 2 proposed by Head Gordon 6 or 7 years apart. They are the same in the sense that they incorporate the same underlying functionale, which is omega B97X. Okay, omega stands for range separated, X stands for exchange, B97, Becky, 1997, random nomenclature. They differ in that both of them have external, non-local, or dispersion terms. XD has an empirical one, XV has an analytical one, and we'll see that they're very similar. They differ in cost by quite a bit, actually, because of that. Okay, both of these incorporate about a dozen parameters, and those parameters are formed by matching a large set of calculated data on energies, geometries, activation energies, a large set of data on small molecules gained not from experiments but from theory. The third set has a funny name. It's called meta-generalized gradient approximation. It depends not only on the density and its gradient, it depends also on the gradient of the kinetic energy, or another way to put that is the second derivative of the energy. So you can think about this as the next example of the Taylor series. The generalized gradient approximation says function density plus its derivative. This one says density plus its derivative plus its second derivative. You now know where to go next. The simplest of these is a functional called B97M. M means meta, dash V. The dash V is the analytical correction for dispersion, non-local. Okay, that's actually the expensive part. There is no X here. This is lacking the Hartree-Fock exchange. So this very simple function has a very strange cost behavior. If you go to a very small molecule, this is very expensive because of this dispersion correction. That it completely is dominated by that. If you go to a large molecule, which would normally be dominated by the Hartree-Fock part, this becomes very efficient. So this method is very inefficient for things like geometry optimization, where you have small basis sets, and very efficient for things like energy calculation, where you need a large basis set. So it's not the molecule size, it's the number of bases. This functional incorporates about a dozen parameters, again, parameterized by the same way. The next shift up is to put the Hartree-Fock part back in. So this is a global hybrid meta. So this is a functionale that is dependent upon the density, first derivative, second derivative, plus a Hartree-Fock part, but without a dispersion correction. Okay, the most common of these, and this is probably the second most commonly used functionale, is called MO62X. M stands for, I think Minnesota, Don Schular's lab. 6 is the year, 2000 is actually 2006. This is something that is parameterized again to a large data set. The number of parameters is about 40. It's very large. This one is widely used. It's respected as one of the best functionality for energy. Were I to show you data on metals, if I were to show you data on metals, you'd discover that it's not very good. But for organic molecules, it's widely accepted as good. The last class, and again, there are many examples of each of these. I'm only going to give a couple. The last class is range-separated hybrid meta generalized gradient. So this says I'm going to put in the density gradient. I'm going to put in Hartree-Fock theory as a variable. In this one, MV, I'm going to put a dispersion correction, which is analytical. This is Ted Gordon. In this one, which is Schular, 11 is the year. I'm going to not put in the dispersion correction. These are very similar. They differ in cost because of that V term. Okay? These are considered, this one is probably considered the best of the modern functionals. It's also the most costly. If you put this in a diagram, it's a little bit out of focus. We have three variables. We have a variable of what to start with. You can either start with the density rho plus its gradient delta rho. That's called GGA. Or you can start with rho plus its gradient plus the second derivative. That's essentially what you're doing. That's called meta GGA. You can now decide what to do about the Hartree-Fock. You can ignore it, don't consider it, and there's really only one functionale that does that in common use. You can call it fixed, it's there, but it's there as a constant, or you can call it variable. So this is increasing complexity as I go from here to here. This is increasing complexity as I go from here to here. The last thing is non-local. What do you do about distant interactions, so-called dispersion? You can ignore it, you can do it empirically, or you can do it analytically. The 7 functionals I described fit into these categories. B3-LIP is starting from GGA, fixed exchange, no non-local. The most complicated one I did, which was, there are 3 of them actually that are similar, the most complicated one starts from meta, variable exchange, evaluate the non-local. That's this one. So you can see that there's some logic here. We've tried to build this logic. Let me flash back for a second. We've tried to build this logic into the program, into the recent editions. As we come here, if you select density functional theories, there's a menu which has a few functionals in it, things that we thought of. Then we go to more, and there's a set of categories. These are exactly the categories they describe. Here's the B3-LIP category. Here's that one. Here's the meta one. You can see that I've only described some. There are many choices. Here's the global hybrid meta one. Here's this one I call best. There are actually 3 choices there. There are many more. There are hundreds of functionals, literally, and that's one of the problems. Because whereas it's easy to propose many, it's very difficult to judge, to really put so many through tests to know which ones are any good or not. Which functional is best? Well, there are 2 criteria. The first criteria is, they're equally important. It's practical. could actually use it. And the second criteria is it's good. Let me give you just the notion of practical in a simplistic way. I'm going to pick a molecule, a modest-sized organic molecule, nitrostrychnine. So it's modest size. And I'm going to ask two questions. I'm going to say, what is it, if we wanted to do structure calculations, let's think about the cost of geometry calculations. That really is the cost of a small basis set. And then let's say we wanted to do an energy calculation, and the one I recommended is this basis set. So what are the relative costs? If you look at the geometry one, that particular molecule has 400 and something basis function, so it's modest. B3-lib is the least costly of the functional, and the other ones are all more costly. The one I'm going to lean on is this one, which is about 2 times more costly. When you get to these ones with analytical dispersion terms, the ones with V in them, those multiply that by a factor of 5. I should just make a technical comment. The reason that there's actually a cost differential is that these are all done with numerical integration. You're actually taking this complicated function and you're not doing it analytically, you're actually solving it with numerical integration methods. And as the function becomes more complicated, you actually need to do larger grid size. You actually have to do numerical integration over far more points. That's why you're actually getting cost differentials. You can see here the one that lacked the Hartree-Fock exchange is rather costly. What this says is that the calculations is not dominated by, in the case of small basis sets, calculation is not dominated by the Hartree-Fock part. It's actually dominated by the dispersion part. And so this one is expensive. Okay, so I now go to the energy question, and the difference is a larger basis set. You can see now that you can see 2 different conclusions. The first conclusion is that all the functions are rather similar in cost. There really are no giant differences. There's small differences. And the reason is that these are all dominated by the Hartree-Fock term. And the method that's missing it is now the only one that's significantly less cost. So when you go to trying to do an energy, try to do some things with large basis sets, and really nothing to do with energy, it has to do with the size of the basis set. You can see that they're all coming down to about the same. There is a small difference, but the big difference is coming down to this one, which lacks Hartree-Fock exchange. Now, I haven't said whether this is any good or not.